Hello, class. I'm not feeling well today, so instead we got a little video lecture for you. We'll try to get through this as quickly as we can. You are going to be pausing every now and then and solving problems, and then hitting play again to see how I solve it. Let's review. Centripetal motion. That happens when you got velocity, and it's perpendicular to some force. When that happens, you execute circular motion of radius r. Ooh. Notice that the force is pointed towards the center of the circle. And your speed and velocity is at a right angle to it. All right, when this happens, you turn a little bit, so now you're going this way, and then 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 you're going this way. Your velocity is always going to be tangent to the circle. And the force will always be at right angles to that, which happens to be towards the center of the circle. When this happens, your net force, which is mass times acceleration, it's also the sum of all forces, if you recall, is now also equal to the centripetal force equation, which is mv squared over r. Yay! That's basically it. Now let's apply it. So this problem is part of notes. 10-kilogram child, 2 kilograms swing. Chains holding the swing are 3 meters long. The child is not moving. Draw me a free body diagram. All right, here we got a box. It is going to be 12 kilograms in mass. 10-kilogram kid, 2 kilogram swing. And you know what? There's a gravity force on it. And there's also a tension force on it. Craziness. All right, what is the net force? Well, kid's not moving. So the net force has to be 0 newtons. If the kid isn't moving, that means the kid isn't accelerating, which means the net force is 0. Now, what is the tension force in the chain? Well, we know what the gravity force is. That's going to be minus mg, which means the tension force in this case is going to be positive mg. Ta-da! Nice and easy. But Mr. Saz, that wasn't circular motion at all. Why did we do that? Set the stage for this! 10-kilogram child, 2 kilograms swing, 3 meters long, but now the child is swinging such that he has a speed of 5 meters per second. Draw the free body diagram. All right. Stay with me for a little bit, and then we're going to pause. Tension force, gravity force. Notice that I made the tension force arrow longer. That was on purpose. That is a hint for you. All right, pause. Solve the problem. And you're back. All right, we know that the net force must be equal to mv squared over r. It must be because, on a swing, you go in a circle, or part of a circle at least. I also know that this has to be equal to mass times acceleration, because that's what net force is. And I know that is also got to be equal to the sum of all forces, which in this case is going to be the tension force minus mg. All right, well, you know what? I don't really care about this for right now. It's irrelevant. Oh, you know what? I can just find the net force with that bit right there. Yay! Because I know the mass. It's 12 kilograms. I know the v. It's 5 meters per second. I know the r. It's 3 meters. What is the tension force in the chain? Here's where this equation comes in handy. Because now I'm going to rearrange it to give me tension force is going to equal mv squared over r minus mg. Sorry, plus mg. Remember, g is positive 10. That's why I had to stick that negative there, because it's, going down. All right, the tension force has to cancel out gravity, and on top of that, make it go in a circle. Huzzah. All right, now I'm going to read this problem. I'm going to give you a little bit of information. We're going to pause again. You're designing a stretch of road that needs a turn in it. The speed is going to be 11 meters per second. The coefficient of friction is going to be 0.5. That's fairly standard. Solve for the radius of the turn. Free body diagram. All right, I'm going to do 2 free body diagrams. Here's the first one. It's a bird's eye view, if you can't tell, but that's supposed to be a car. We know that its velocity is going that way. It needs some force on it that way. All right, and now rear view, license plate. All right, I know that I'm going to have a gravity force on it down, and I'm going to have a normal force on it up. It's driving into the screen here, and it's going to have some force that way. I wonder what it could be. All right, at this point, you're going to try to solve for the radius. Pause. And you're back. All right, so let's see here. This force, that's going to be friction force. Gravity and normal force, they're going to cancel out because I'm on a horizontal plane, which means my net force, in this case, is going to be equal to the friction force. Remember, the equation for friction force is mu k times normal force. In this case, normal force is mg. Since that's my net force, and I'm going in a circle, it's also going to be mv squared over r. M's cancel. Solve for r. All right, I'm going to multiply r over there. I'm going to divide all the stuff over there. I'm going to be v squared over mu s. Technically, sorry, I wrote a k there, but it's an s. G. Ta-da! All right, next torture device. I mean example problem. All right, in review, what we know is this. When velocity is perpendicular to your net force, you go in a circle. That means your net force is going to be equal to the centripetal force, which is mv squared over r. In addition, stuff that is always true, F net is m times a. F net is the sum of all forces. That's it. This is everything you need to know to solve all of these problems. Let's see how you do on challenge problem number 1. David versus Goliath. So, old story, David here has a rock and some strings, and he's swinging around in a circle over his head. Rock has mass m, swinging with radius r at a speed of v, and it's making some unknown angle at the horizontal. All right, let me redraw this. So there's his arm, there's his hand. Beautiful, I know. So good at arts. All right, and he's swinging it over his head, except he's not, swinging in a perfect horizontal circle like the picture shows. It's actually going a little below horizontal. I'm over-exaggerating here. And now the ball is, or rock, is going into the screen and out of the screen in a circle. Yay! All right. That's all you get. Please solve for the tension force in the rope. Then solve for theta. Pause. You're back. All right, solve for the tension force. Okay, well, let's look what's going on here. I got a gravity force down of magnitude minus mg. I got a tension force there. But check this tension force out. This y component of my tension force, it has to cancel out gravity. It has to. Otherwise, the rock would fly away. Okay, so I know that. Oh, you know what? That really only leaves one force, because if this component gets canceled out by that force, all that's left is this. This has to be my net force, my centripetal force. All right, cool. Problem. That's going to be ft sine theta, assuming that's theta, and this is going to be ft cosine theta. So first I got to solve for ft, mg over sine theta, plug it in there, and then I will get my answer for tension force.